In the last video, I discussed the notion of what an infinite series was, and I introduced this concept of partial sums, or I hinted that this was an idea we were going to look at. So I want to talk about what a partial sum actually is. So I'm going to talk about the kth partial sum of a series, sum n equals 1 to infinity a sub n. The kth partial sum of a series I'm going to denote by capital S sub k. And this is going to mean the sum of the first k terms of the series. So rather than adding up infinitely many terms, I stop at k terms. So it's the sum of the first k terms. If my indexing starts at 1. So we'll in general use that subscript to mean that the last term I've added is a sub k. Notationally, we can write this as follows. This is the sum n equals 1 to k of a sub k. That's another notation for sk. And so we can think about what this might look like. So for the first series listed, the series n times 1 over n times n plus 1. And so for this series, the first partial sum is just the first term by itself. Second partial sum is the sum of the first two terms. So 1/2 plus 1/6. The third partial sum is the sum of the first three terms. 1/2 plus 1/6 plus 1 over 3 times 4, 1/12. S4 is 1/2 plus 1/6 plus 1/12 plus 1/20. And for each of these, I could then try to combine it into one fraction to get a sense of what's happening to the numbers. So 1/2 plus 1/6 is 4/6. I'm purposely not going to reduce yet. 1/2 plus 1/6 plus 1/12, the common denominator here in this case, I can have everything be over 12. So 1/2 is 6/12, 1/6 is 2/12, so that's 6/12 plus 2/12 plus one more 12, 9/12. Here, the part from here, remember, was 9/12. Now I have to add 1/20. To get a common denominator, I need a number that 20 goes into as well as 12. I'll just go with something big that I know goes into both of them, maybe 120. 1 over 20 is 6 1/20ths, and then 9 over 12 is 90 1/20ths, so I'm getting 96 over 120. Let's see, maybe if we can reduce that a little bit. That seems a little out of control. Both of them are divisible by 3, so dividing by 3 I get 32 over 40, so on and so forth. So the question is, does S sub k have some pattern for which I can write down a formula, and moreover, is there a trend in what's happening to the values? That's the real question I want to ask myself. So 32 over 40, let's actually reduce this further. Okay, so 4/6 was 2/3. 9/12 is 3/4. 32 over 40, both are divisible by 8 right now, and I get 4/5. So what we actually see is it looks to me like the sum of the first n terms. Is it possible that this is the quotient of consecutive numbers? And notice here the numerator is 1 for the first term, 2 for the second term, 3 for the third partial sum, 4 for the fourth. And so it looks like possibly the formula here is that the sum of the first k terms might be k over k plus 1. We're going to be able to check that and see if that makes sense. Additionally, we're going to look and see then whether or not that means it converges. So we're going to define the sum of a series as follows. If the sequence of partial sums of an infinite series converges, and the limit as k goes to infinity of s sub k equals some finite number s. So remember, if a sequence converges, we call the limit of that sequence. That's what this s is representing here. So it's representing the limit of these partial sums where I add term after term after term. So if this is a finite real number, then we say that the series converges. That the series n equals 1 to infinity of a sub n converges. or is convergent, and we call S, the limit of its partial sums, the sum of the series. In other words, we write that the series n equals 1 to infinity of these terms a sub n is equal to this number S. But if the sequence of partial sums is divergent, we say the series is divergent. So, looking at our example here, we notice that the limit, the sequence that we're talking about here, k over k plus 1, that's the sequence of partial sums. We had the series n equals 1 to infinity of 1 over n times n plus 1. And we notice that its kth partial sum could be written as k over k plus 1, and that the limit as k goes to infinity of k over k plus 1 is going to be 1. You can see this either by applying L'Hopital's rule or by dividing everything in sight by k, and then you can see this is 1 over 1 plus 0, which is 1. Let me make it look pretty again. Therefore, in our example, I'm going to say that the sum of the series, the infinite series, if I added up all the terms, will equal 1. Let's investigate that on Desmos and see if that's what we observe. So here we are in Desmos. I've written in the sequence that we're talking about 1 over n times n plus 1, and we're looking at the sum of terms of this sequence. So the notation I have here in this red line, it's plotting for every n, it's going to plot, or in our case we were calling these k's, it's going to plot the sum of the first n terms of the sequence. So we start out and we just have the first term. Here I've plotted a few more. So the 2, 2/3, 3, 0.75, 4, 0.8, 5, 0.083. As I drag it forward, you can see we're adding more terms. It gets a little crowded here. So let me take the label off for a minute. But we can see that they are converging closer and closer. The values are getting closer and closer to the number 1, which is what we expected the limit of this sequence of partial sums to be. So this is how you might investigate this on Desmos. You can also investigate this in Excel, and I wanted to show you that quickly. So here I am in Excel, and to start out, what I'm going to do is I'm going to just put all the counting numbers down here. So then the pattern that we wanted to start out with is we wanted the nth term to equal, here I'm going to put the terms of the sequence. So I'm going to have 1 over n, which is just the value at that level, times n plus 1, so a2 plus 1. And then from here, if I drag this, it'll take that formula and adapt it. So we can see we are getting the correct values. So this is 1/6, 1/12, 1/20, so on and so forth, going down. Now to do the n partial sum, what I want to do is add up all terms up to, from the top up to a certain point. So I want to do the sum of this term. I'm going to put a $sign right here. That's what fixes that, up to the term I'm currently at. So in the first line, the first partial sum is the same. But now if I drag to the next one, you'll notice from the notation here, now it's going from B2 to B3, so it's summing both of these. If I drag this formula further, this is summing, like we look at term 9, this is summing the term from B2, which is the first one here, all the way down to B9. So it's the sum of the first 9 terms, etc. We can see, I got to keep dragging here. We're going to have to keep increasing the pattern so we can see what's happening a lot further out if we really want to see the trend. And then I can drag here to continue to indicate terms of the sequence. See, eventually they get to the point where they're a little hard for Excel to distinguish from 0. And here I'm going to keep dragging down the sums of, so the partial sum values. Let's go about there. you'll see it is converging fairly slowly. I mean, I'm still only at 0.992. Even down here at 172, I'm at 0.994. But the values are getting closer and closer to 1. This series slowly trudges on to getting a final sum of 1. But notice if I've gone this many terms, I'm making a pretty gross assumption if I say that like something that once I add the first 114 terms is at 0.991, that the overall sum must be 1. If I hadn't known what the formula for the series was and seen the pattern in the way the values showed up, it might be a little difficult for me to say that actually the value of the sum of the sequence is in fact n over, that the kth partial sum is k over k plus 1 and that the limit of the sum is 1. But I can check my formula too. I could see, did my formula work? And I could do that just by writing it in here. I want this term divided by this term plus 1. I'm going to need parentheses. And I can check and see if I have the right formula because I'd expect it to align with the nth partial sum. I'm not going to drag that one forever, but we can see that we do have consistency. So Excel can be a really nice way to examine this if you don't want to do it visually. Sometimes the visual makes it easier to see if the values are really flattening out though. So that's how we define the sum of a series and what it looks like in a case where it converges.